Okay, sorry for the interruption. I've just shifted myself more to the right hand side as I realized that I was kinda blocking some of the workings. Okay, so earlier we were talking about how to calculate the value for small p of small p. So you can see over here we were last stuck over here. Okay, let me just pick my pencil. Yep. The last part we start on was over here. So we need to remember that this algorithm to calculate P over here, then let me just write it over here. It can be used to calculate small p or small t. So if you want to calculate small t, you just basically replace small p with t in the code, and the logic is still the same. Okay, let's start on a new page. So earlier we had this, okay, to calculate small p, we'll use this algorithm. Okay. So remember this asterisk means multiply. Sorry, it was like this. And we can see over here, if we were to distribute this as, in this case, it will be theta of 1, because this is already theta of 1, and this addition is another theta of 1, so it will be theta of 2, which is equals to theta of 1. Yeah. And then this is also theta of 1. And then when you want to figure out the time complexity, it will be, in this case, it will be it will be theta m, because Tc is equals to theta of 1 plus number of iterations of the for loop multiplied by the time complexity per iteration. And this remains as theta of 1, and the number of iterations is m minus 1 multiplied by the time complexity per iteration is this. So we'll have theta of 1 plus theta of m, and theta of m will dominate, so you simplify the theta of m. So this means that both p and t can be calculated within theta of m time. Because remember, this algorithm that we see over here can also be used to calculate t as well. Okay? So let me just write here. This triangle can be used to calculate t as well. Yeah. But one thing that we actually later also realize is that when we want to convert, actually, let me see whether I can put it all over here. Okay. Actually, let me just select object. Yeah, so we want to convert the first pattern, which is of length m, to a number p. You take theta of m, as explained earlier. And when we want to convert the first m characters in p, the first m characters in t, which is the first text window, to a number, it will also take theta of m, but subsequently it will take O of 1, big O of 1 in linear time, which we'll explain in the next slide. Okay, so what I mean is that, let's say you're given p, and then, it can be like any number, maybe it can be 1, 2, 3, 4, and then maybe it'll take theta of n to calculate p. And let's say t is longer, let's make it twice as long. Yeah, so 1, 2, 3, 4. Actually, let me use a better number. Yeah, 8, 7, 6, 5, 1, 2, 3, 4. So we want to calculate the small t value for the first text window. You take theta of m. Okay, but subsequently, when we want to calculate the second window, and let me just redraw it over here. So this is the second window. 1, 2, 3, 4. Wait, 1, 10. Correct. This will only take O of 1 instead of theta m. And the same logic for the next window, it will also be O of 1, so on and so forth. Yeah. Okay. So how can we do this? How can we ensure that the subsequent parts will all take O of 1? And it's actually very straightforward. So let's move on to the next slide. Okay, so for example, let's say our t is this number over here. I'll just avoid drawing the cells because that will take a lot of time. And so let's say we calculated the first t value over here to be 364,152. Yeah, and this is, we're just assuming in this case it's base 10. And let's say we want to calculate the next t value of the next window, which is over here. Okay. Wait. Here I made a slight mistake. Yeah, let's do this instead. Okay, let's say this is the first window and this is the second window. Okay, so the window is 5 characters long. And this first window has a value of 36415, which takes theta of m to calculate. And this is the second window. And what we can do, instead of doing this code that you see over here, which will take theta of m, we can avoid doing this and we can do something else instead. It's actually really intuitive. So we can just take the OT value, which is 364152, minus the value of the most significant bit they had. So it will be minus 30,000, okay? And then we'll multiply it by 10 and we'll plus our new digit. Yeah, so this will be your least significant, LSD is your least significant digit. Okay, so how do we translate this into code? So it means that our new t value for the new window is equals to the OT value, which is 364152, minus I think this was the most significant digit that we had. And this is the most significant digit of the old window, multiplied by d of m. Okay, and so what is d of m? Okay, so d of n is equals to ministries. We can do this. We're trying to calculate the highest power that is involved in the multiplication. So maybe we'll need to pre-calculate the highest power beforehand, because if we do so, we need not calculate it afterwards. So d of n is equals to d of m multiplied by d. Yeah, and just note that dm is actually equals to d to the power of m minus 1. But we can't really write this in code, which is why we wrote this instead. So in this case, what this code over here allows us to obtain the most significant power. And this is IE 3 times 10 to the power of 4. Which makes sense. Because we can see over here, over here is 4, and there are 1, 2, 3, 4, 5 characters over here, so it will be m minus 1, which is 4, which is correct. Now maybe I'll also draw it out here as well. Yeah, so dn is the power of your most significant digit. It's correct. Because if let's say it's 364152, and this is the first window is 36415, and let's say this over here has n equals to 5, then this is equals to 3 times 10 to the power of 4. which is equals to 3 times d to the power of m minus 1. So we need to calculate m minus 1 via the algorithm that we have over here. And so back to what we were talking about earlier. Here, you just need to put a bracket here. And we'll multiply my d. And then we'll see. Then this is ending our least significant digit. And in code, it will be like this. We'll reuse the same t variable. First, we're just updating the value of t. And this is I will be over here. So remember, I is the pointer to the window that we're currently at. So in this I is still pointing to the old window. Okay, so I is pointing to the first character of the old window, which is what we want. Okay. And in case you are still not sure what I is, do refer back to my previous video about the naive algorithm, where I covered what I is specifically within the first 5 minutes or so. Okay. Multiply this by d, and we'll plus, and the LS, the least significant digit, aka our LSD, is basically at index I plus m, because if I is over here, and we know that 2, 3, 4, 5, and we know that m is 5, then I plus 5 will just give us the LSD. First, remember, again, you can refer back to my previous video on the ninth algorithm where I cover what n is within the first 5 minutes. So m is equals to the length of p, which is basically the length of a window. Okay. So here, I'm just going to reiterate what this allows us to do is this. So you raise to convert the first pattern to a number of small p, which is theta of m. Okay. Let me just select my pencil. Just give me a sec. I think there's something wrong with my. Oh yeah, remember I found my pencil. Sorry about that. Okay, so it converts to theta of m, and subsequently for small t, for the first window it will take theta of m, but for the little windows it will just take linear time O of 1 because of this line. Because this line effectively, okay, let me just erase this over here. So m equals to length of p, and this will take O1. Or if you say theta of 1, yeah, in this case. But now there's another thing we need to consider is what if the pattern is long? What if P is long such that M, which is the length of P, is very large. And we should see that this will cause, it means the resulting number P or small t will be enormous, which will lead to buffer overflow. Because remember, we can't store super large numbers within like buffers, which are basically temporary places that we use to store values. And why is it enormous? It is because if you look at the code earlier over here, you can imagine that if M is large, then remember this, let's say for example, this loop over here. If M is large, then this for loop will run many times such that we keep on multiplying the numbers more and more to the point where the number is way too large to store the value. Yeah, and we can see in the code over here as well. If M is too large, then obviously our small p and small t will be very large as well, which is not what we want. So this makes us wonder, what is the solution in this case? This is the solution. We have to move on to the next slide. What we can do is something called hashing. So if you have done hash tables before, then this will be very easy to understand. So basically, for what we do is hash the pattern to a number. Instead of p, it will be hp. So this is the hash value for p. And then we'll hash the first window, which is n characters to a number ht. So instead of just small t earlier, now we have ht. And then if hp equals to ht, we'll just compare the pattern character by character with the text window. And equal is found and we exit. Okay. Else, if it's not equal, then P. Hey, no, I should just say go to step 4. And if HP isn't equals to HT, else go to step 4. So if HP isn't equals to HT, we also go to step 4. We check if it's end of text. EGA whether this is the last window. If yes, then the pattern isn't found. Because if this is the last window and we've already checked it, that means there's no other windows left to check. And therefore the pattern isn't found. Else, if the pattern isn't found yet and it is not the last window, then we just shift the window one to third. Then rehash it to another. No, actually, no, I should just say rehash it again. Because it may end up being rehashed to the same number. But the key step is that we rehash it again. Again to jet. So we rehash it again to the updated HT. And this rehashing, okay, remember we said that you take O of 1 because of the previous slide. And after we rehash, we go to step 3. Yeah, so this is the key algo. And one thing I forgot to mention was that, remember how in the previous slide I mentioned this algo to calculate the power of our most significant digit, d to the power of n minus 1. Okay. We calculate this once. Okay. Because we'll be raising it many times later on, because whenever we want to update the value of HT, we'll need to use d to the power of n minus 1 because of, you can see this line over here. Yeah, we'll be using this line very often whenever we want to calculate the new HT value. The only difference is that now that we'll need to update it with some hashing involved. Okay, so to reiterate what hashing is. Okay, so sorry, I should have defined this earlier. Hash means we hash a value, means we take it mode point number 2. So we take it and we mod it by a prime number q, and it should be large. And why is large? Well, I'll explain it in a moment. Yeah, so for example, if let's say q should be larger than 13, but I'm just using a smaller q here so it's easier to calculate. And let's say if I just have 5 mod 13, they give me 5. So this is what hashing is. It's basically you're given your original number and then you mod it with another number to get a result. Yeah, so this is what hashing is about. And one thing I want you to take note of is if HP equals to HT, does it mean that P is the same as the window that we're currently at? And the answer is no. And that is because, okay, let me just write here, does not mean that P matches that window. Because, for example, we can have, let's say, if Q is equals to 13, HP or H and V equals to, let's say, 5, okay, and HT, the hash value of our common windows equals to 18. And 5 mod 13 is equals to 5, but 18 mod 13 is also equals to 5. So even though both of their sorry, wait, this shouldn't be like this. This is HP and HT. And these are the original numbers that we had. Okay, so this is P. I just say this is small p. And this is small t. So even though their hash values are the same, but p is actually not equal to t plus 5 not equal to 18. Which is why we need to compare the pattern with the text window one by one, like we did in the naive algorithm. And another thing is, why should the part number be large? So it should be large because we want to reduce the number of cases where HP is equals to HT, but P doesn't match the window. So it's basically like a false alarm. And this phenomenon is also known as spurious hits. And later I'll just show you an example of how this works. We'll take a break for now.